Welcome back, everybody. So now let's look at the logical axioms. So the way we set up our formal deductions was by applying only one rule, modus ponens, and the logical and start from the logical axiom and the assumptions that could be whatever assumptions you want, right? So you start from logical axioms and your assumption, and you apply modus ponens, and that's how you do your rules. By the way, this is only one way of doing this. Actually, you can take different logic books, even introductory logic books, and you will see all different kinds of methods. Mostly, the variation is on how many logical axioms you use and how many rules. So sometimes people like to have many rules instead of just one, and like very few logical axioms. And sometimes, like in this case, we have many logical axioms. Well, six, a group of like 6 types, infinitely many actually, and only one rule. So I don't know, you gain and lose on different kinds. They are all equivalent. All these methods are equivalent of defining formal rules, formal deductions. That's the one we're using. Okay, so modus ponens is very simple. So what are the logical axioms? So okay, so before defining logical axioms, I need to define this notion. Is very simple. I just say that a formula phi is a generalization of a formula psi if phi is of the form for every x1 for every xn psi, where x1 and xn show up inside the formula psi probably as free variables, but maybe not necessarily, but you may think that these variables here showed up inside here, and here they were free variables, and now they get bounded by these quantifiers. Okay, so it was here you have some free variables. The generalization means you just put for alls up front for all those free variables. It's just gonna make the notation a bit cleaner to use this notion. Okay, so here are the logical axioms. So the logical axioms are the generalizations of the following formulas. Tautologies, which we're gonna see in a few minutes. What they mean, but essentially they are the tautologies from sentential logic translated to first order logic, and of course generalizations of that. So you can take a tautology and put for alls up front. The formulas of this form. So this is an infinite. So these are all infinite set of formulas. These are groups of axioms because there are infinitely many tautologies. There are infinitely many of these formulas of this form. This is for any well-formed formula alpha. You consider something of this form. Where this means alpha where x is being substituted by t. And you're only allowed to use this when t is substitutable for x in alpha, and we'll get into that in a couple of minutes in this video. The next one says that if for every x, alpha implies beta, and alpha and beta are again well-formed formulas, and you have to imagine that x shows up as inside alpha and beta, otherwise it's kind of trivial. But imagine that they show up as free variables inside. So if for every x alpha implies beta, then you know that for every x alpha implies that for every x beta. And again, this is a whole family of axioms, one for each pair of well-formed formulas alpha and beta. Number 4 says alpha implies for every x alpha in the case where x does not occur as a free variable in alpha. Okay, so essentially these guys don't mention x. So this for all x ends up being like a dummy quantifier. Yes, for technical reasons it's there, but it's a dummy because there is no x to quantify in here. And actually there are 2 more in the that are about equality. These are kind of the ones that are logical in general, and then there are the ones about equality. One is that x implies x equals x, sorry. That's obviously. And the other one is that x equals y implies alpha equals alpha prime, where alpha prime is an atomic formula, and alpha prime is obtained from alpha by replacing x in some places by y. Okay, so you know that x equals to y, so an x shows up somewhere inside alpha, and you can replace some of those, so long as it's free, where it's free. We know where it's bounded by y. So you have to be careful. Don't replace spots where x is bounded. Only, and you don't have to replace everywhere. Okay. So for instance, if alpha is of the form x plus x equals 1, then axiom 6, in the instance of axiom 6 in this case, becomes x equals y implies x plus x equals 1 implies x plus y equals 1, right? So here is alpha, and here is alpha prime. Okay, so each of these groups is a group of axioms. There are infinitely many because you're taking all the possible well-formed formulas alphas, and these are the logical axioms that you can just put anywhere in your deduction for free, always. So there isn't too much to say. I guess these are very self-explanatory of what those things are. Let's talk a little bit about what this means, and then let's talk a little bit about what tautology means. Okay, before that, let me recall that exists x is defined as not for all not. Remember, in Enderton's book, for first order logic, formally we only have one quantifier for all, and exist is just defined out of for all using that equality. That's why all these axioms we're only using for alls, right? So there are only for alls and the generalizations of these guys. So they can all have for alls up front. There are no exists in here, but that's because we can define exist from for all. So we don't need to put it in the rules. Okay, now yes, let's go to substitution to figure out what that means. So x alpha t, that's what showed up there in the group of axioms 2, is obtained from alpha by replacing x by t whenever x occurs free. Okay, so it has to be I guess wherever x occurs free would have been better. You just take the x and replace it by t, and in this case it's not just some places like we did in here that we chose to replace it in this case but not in the other case. Here we are just replacing everywhere that occurs free. Okay, that's what you do when you write x alpha xt. Okay, so that means alpha, like find the x's, replacing for t's, where t is a term. So here t is a term, this is a variable, and this is a well-formed formula. Okay, so for example, here is your formula alpha, and q and p are predicate symbols, relation symbols that are in the vocabulary, whatever the vocabulary is. And it says here replace by x by y. So what you're gonna obtain is q of y implies for every x p of y. No, because of this line up here, whenever x occurs free. So here x is not free because x here is bounded by this quantifier. So that one we don't replace. Okay? So here x is free and here x is bounded by that for all. Okay, so you only in the case where it's free is that you replace x by y. What about the following example? Suppose alpha is of this form. It says for every y, not for every y, x equals y. So essentially it's saying x is not the only guy in the whole world, the whole structure, whole universe of the structure. It's not true that everybody is equal to x. And then notice this is essentially instance of group 2 in the axioms right here. for t equals y. Let's see what we get. Well, we are gonna get for every x alpha, not for every y, x equals y, implies, and now we have to replace x by y in alpha. So here in alpha, this one is free, right? Because there is no quantifier over x, so we can just change it freely. So this is for every x alpha, and here we're going to do alpha x y, and we're going to get not for every y, y equals y. Okay, and we can rewrite that in terms of exist. For every x, there exists y, x different than y. Okay, and then implies there exists y, y different than y. This looks odd, right? So how do we interpret this? This is essentially says for every x there is something different. So it says essentially it says there are more than 2 elements in total. Right? That's always true so long as there are 2 different elements in your universe. For every x there is somebody different. This is always false. There is no y that is different than itself. So you have something implies false. So essentially this is only true if there is only one element in this whole structure. While this is supposed to be an axiom, right? A logical axiom. And now we have something that is only true if the structure has, so overall, exactly one element. So that's not good, right? An axiom should always be true. It shouldn't tell you anything about the structure you're talking about. It should be just something that is always true. And this is rarely true, that this sentence up here. So something is wrong. And if you see axiom 2, it's exactly this thing that we said for every alpha, but only if t is substitutable for x in alpha. And what's going on there in that example is that y is not substitutable from x in this formula. Why? Well, because this formula alpha has y up here, it has x up here, and if you change it by x, there's the x by the y, now this one becomes bounded to this quantifier, right? So in the substitution, now this, which was the x here, became bounded by that. While in this one, it was free. Originally in alpha, it was free, and now it became bounded after the substitution. And that's not good. That's messing up the whole idea of substitution. So it's not good to make substitution like this. If you want to change x substitute for something else, and that's all bounded by a y quantifier, you shouldn't use a y. So the definition is the following. So you say that t is not substitutable for x, so t is a term here, in alpha, if inside t there is a variable y in t that gets captured by some quantifier, either exist or for all, when you do the substitution. Okay, so for instance, here once we did the substitution, the t here is just the y alone. The y became captured by this quantifier, and that's not good. So if something gets captured by a quantifier, then it's not substitutable. So let's look at a couple examples. So first, let's consider here is our term t, and these are formula alpha, and we want to substitute this for y, t for y. So let's see what the substitution is. So if you do the substitution, we are going to get there exists an x such that, and now the y is going to be substituted by x plus 3 equals x plus 1. Right? So now this variable here that was part of t, this is t, here is t. This variable here became bounded by this quantifier, became captured by that quantifier. So this is, the answer is no. This is not substitutable because we input a variable here in place of y, which was bounded. While the y was free here, now it has inside something is bounded, so it's not good. Right? Let's look at this case. Now we are gonna, it looks a bit weird that we're gonna substitute something that this t that contains y for y in alpha, the same alpha. Let's see what we get. So first let's do the substitution. So if you substitute that term for y, you get there exists an x such that y plus 3 equals x minus 1. And now this one stays free. So there is no issue. It's no issue here, right? So no variable inside our t becomes captured. So yes, that one is substitutable and we are fine. What about this one up here? So now this is t and all of this is alpha, and z shows up there and y shows up here. So z is quantifier here. Let's see what happens. So let's write down the substitution. So the substitution, we are gonna get for every z different than x, and there exists an x, and let me just do red for the substitution. C plus 3 equals x plus minus 1. Okay, so that's what we get. And now, are we bounding any variable that we didn't want to bound? Well, no, this c here stays free because this here, the for all c is only working inside these parentheses, right? So it's not working outside. So this one up here is free, right? This c up here is bounded, but the one that show up inside the term did not get captured by this quantifier. This one is still free. So yes. So the answer is yes. This is substitutable because we are not mixing up the variables. Okay. So this is the definition of substitutable that we need for that group axiom number 2. It's in general is like the rule will be informally will be like just don't do weird stuff with the variables. It's trying to avoid that. Formally, this is what it is. If you want to program it in a computer, you have to know how to do this. But essentially, it's saying just don't do weird stuff with the variables. Don't mix up variables that shouldn't be mixing. So that you put a meaning to something because it already has a meaning. So if you stay using different variables, everything should be nice and clean.